All right, welcome back to Chapter 5. This is Part 2. Okay, we have been talking about energy and internal energy, work and heat, and now we're going to turn to another pretty important thermodynamic property called enthalpy. Okay, and enthalpy is just the total energy of the system, which accounts for expansion of the system. So when we talk about enthalpy, designated as H, it's equal to the internal energy plus the product of pressure times the volume. Okay, so it really allows us to discuss heat flow in a process that occurs under constant pressure. So enthalpy, like I said, is equal to the internal energy plus the product of pressure and volume. Okay, internal energy, pressure, and volume are all going to be state functions. So we can also look at the change in enthalpy under constant pressure, which we can define as delta H is equal to delta E plus P delta V. Well, if we take a look at an example system, okay, to really understand what we're looking at here is basically if we take zinc metal and we react in that with acid, hydrochloric acid, okay, if we remember back to chapter 4, that means that we produce hydrogen gas, okay. Now if we assume that the pressure in the system, okay, is the same as the atmospheric pressure, this means that the piston, okay, so there's a little piston here, is going to rise, right? Basically, it's going to rise because you're having hydrogen gas being produced, okay? And so then the system, everything inside, is doing work on the surroundings, okay, by pushing against the atmospheric pressure in order to raise that temperature, or raise the piston. All right, and so the work that's involved in the expansion or compression of a gas, okay, is called pressure volume work. Well, this pressure volume work under constant pressure can be defined as the work, which is equal to minus P delta V. Okay, so P is the pressure, V is, or delta V is just the change in volume, final volume to the initial volume. Okay, so if we keep this in mind and we kind of return back to that whole enthalpy discussion, okay, what we're really trying to understand is what happens at constant pressure. What happens under constant pressure in these systems? All right. Well, we know that delta H is equal to delta E plus P delta V, right? And we defined the internal energy, the change in this internal energy, previously back in chapter 4 as the amount of heat plus the work done on the system. So if we substitute in Q plus W for delta E, we basically get that delta H is equal to Q plus W plus P delta V. Now, we just said that the work involved in the expansion or compression of a gas is equal to minus P delta V. So if we substitute in minus P delta V for the work here, we end up getting delta H is equal to Q plus a negative P delta V plus P delta V. So those two cancel and we're left with delta H is equal to QP. So therefore we can say that the change in enthalpy of a system under constant pressure is equal to the amount of heat gained or lost. Okay, and so this Q we know is heat, but that little p just means under constant pressure. Okay, so delta H is just equal to the amount of heat under constant pressure. Well, if delta H is positive, then the reaction is gaining heat, and we call that an endothermic reaction. Okay, if delta H is negative, then the reaction loses heat, and it's called an exothermic reaction. All right, so the delta H for the reaction is just called the enthalpy of reaction, okay, or we can call it the heat of the reaction, and it's just equal to the enthalpy of the product minus the enthalpy of the reactants. So for an example, we can take and say that 2 moles of hydrogen gas, okay, react with 1 mole of oxygen gas, and we form 2 moles of water, okay, and the delta H for this reaction is minus 483.6 kilojoules. Well, that negative sign says that the reaction is exothermic, which means that heat is being released to the surroundings. And we can see that when basically we take a balloon filled with hydrogen gas, is ignited, basically it reacts with the oxygen in the air, and you get an explosion, right? So heat is being released to the surroundings. All right. One thing to note is that this delta H is talking about that we have 2 moles of hydrogen gas, okay, or 2 moles of water has that delta H. So when we're talking about the enthalpies of a reaction, enthalpy is an extensive property. okay, which means it's dependent on the amount of material. Okay, we defined that back in chapter 1. Right. Well, there's really a couple things here that we need to know. One is that enthalpy is an extensive property, okay, depends on how much of the material is available. Secondly is that delta H for a reaction in the forward direction is equal in size, but opposite in sign to delta H for the reverse reaction. Okay, so if we go back quickly, basically the reverse reaction of water breaking down to hydrogen gas and oxygen gas is going to be a positive 483.6 kilojoules. Okay, so back and forth. The third thing is that delta H for a reaction depends on the state of the products and the state of the reactants. So for an example, if we took the combustion of methane, CH4 gas, okay, reacting with oxygen gas to form carbon dioxide and water, right? The delta H for the reaction in the forward direction is minus 890 kilojoules, okay? And that means that that's for 1 mole of methane, right? Because we have 1 mole here. But if we had 2 moles of methane, so a 2 is coefficient of 2 in front of the CH4, then it would be twice as much for the delta H, okay? So keep that in mind. Okay, so now that we've defined enthalpy, okay, we need to learn what methods are used to determine the value of this change in enthalpy experimentally, okay? So this can actually be done by measuring the temperature of the reaction under constant pressure. Well, under constant pressure, we know that the enthalpy of the reaction is just equal to the heat flow, right? We just said that delta H was equal to QP. So the measurement of heat flow is just called calorimetry, okay? And we use what's termed a calorimeter in order to measure that heat flow. So you're going to actually use a calorimeter in the laboratory similar to the one that's shown here in this figure, okay? Basically you have a styrofoam cup which is going to insulate that reaction, okay? You put a reaction mixture inside, okay? And then you put a thermometer down into that reaction to monitor the temperature change when these two reactants combine, okay? Well, in calorimetry, basically these substances, okay, different substances will basically change temperature when it's heated, right? But the magnitude of this temperature change really varies between the substances. Well, the amount of energy that's required to either raise the temperature of a substance by 1 Kelvin or 1 degree Celsius is what we call this heat capacity, okay? And we can be a little more specific and say, okay, we define what's termed as specific heat capacity, or we call it specific heat, and it's abbreviated big C, little s, okay? It's the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin or 1 degree Celsius, okay? So this is more specific, right? So that's why it's called specific heat capacity. We also have a molar heat capacity, which is big C, little m, and it's the heat capacity of 1 mole of a substance. Well, the specific heat value can be determined experimentally by just measuring the temperature change that a known mass, okay, undergoes when it gains or loses a specific quantity of heat, okay? And this S, which is really big C, little s, okay, the specific heat, is equal to the heat transferred divided by the mass of the sample times the change in temperature, okay? And some specific heats are given to you down here at the bottom. Well, when we look at some different types of problems, okay, you're going to see that these are constant pressure calorimetry problems, okay? And so calorimetry can tell us A, if the reaction is exothermic or endothermic, okay? But it really allows us to calculate the heat of the solution or the heat of the reaction, okay? And so under constant pressure calorimetry, basically we can say, we can rearrange this equation, which we had back here, to just say, okay, well, we're measuring the heat of the solution, right, which is part of the surroundings, okay? But that heat of the solution is just equal to the specific heat times the mass of whatever sample times the change in temperature that was measured, okay? It's Q of the solution. Well, we know that basically the heat of the solution and the heat of the reaction, okay? The heat of the reaction is our system. And so the system and surroundings have opposite magnitudes, or have the same magnitude but an opposite sign. And so we can say that Q of the solution, or Q of the surroundings, is equal to a negative Q of the reaction, or Q of the system, okay? So we can use this equation in order to calculate for constant pressure calorimetry problems. Well, Now we can turn to what's termed constant volume calorimetry, okay, bomb calorimetry, which is a bit more complex, okay, but the calculations are actually a bit easier, okay. So a bomb calorimeter is used to study combustion reactions, right? Combustion reactions are basically something reacts with oxygen gas to produce carbon dioxide and water. Well, basically, as you can see in this figure, you have a very insulated container, okay, it's filled with water, and then you have this little reaction chamber, okay, which basically you put your reactants into, okay. The reaction chamber is then wired with basically an ignition source, and basically upon detonation of that reaction is going to proceed. You're going to have that combustion reaction take place, an explosion, a bomb basically, and the, whoops, sorry about that, okay, and so basically the you have that reaction that proceeds, and the temperature of the water outside the reaction chamber, so everything out here, okay, is measured in order to determine the amount of heat lost during the reaction, okay, and there's a little stir in here to keep things moving around. Well, to calculate the heat of combustion, what we want for these types of problems, we're going to measure the heat of combustion, okay, the enthalpy of the reaction. And so we need to know the total heat capacity of the calorimeter that's being used, okay, as well as that temperature increase, okay. Well, the heat capacity of the calorimeter is actually determined experimentally, and in most problems I'm going to give it to you, okay. Pretty much all problems I will give you that, okay. Well, the heat of the reaction then, Q of the reaction, is just equal to this negative specific heat capacity of the calorimeter times the change in temperature. That's it. So it's pretty straightforward for those. At this point, this is going to conclude part 2. Part 3 is a few more calculations. It's pretty brief as well. So I'll see you back then.